Hello, we will continue our lecture on the process integration for energy recovery, and this is the last lecture under that topic. Today we will be dealing on the utility system design and optimization. Here I will introduce a new tool called the Grand Composite Curve, and this tool is particularly useful when we are trying to select hot and cold utilities for our system. So I have mentioned before that the common hot utility system is the steam, adding steam to our process. But there's another hot utility system, which is the hot oil system. So steam system is commonly used as hot utility. Here we have high pressure steam or high or sometimes medium, and we also have low pressure steam options. Um, as for the hot oil utility system, we use hot oil, a stream of hot oil to heat our process. For cold utility systems, as I've mentioned before, the most commonly used is cooling water system. Um, it's used to reduce the temperature of the stream to ambient, okay, to ambient temperature. However, if we need to further reduce the temperature to below ambient temperature, then a refrigerant system may be used. Let's use the previous example to illustrate how we can select utility for our process. In the previous lectures, we have done targeting for this particular problem. So remember that we need 7.5 megawatts of hot utility to raise the temperature for the cold stream to its targeted temperature, which is 230 degrees Celsius. And we also identified the minimum cold utility needed, which is 10 megawatts energy to bring the hot stream temperature down to 40 degrees Celsius. And the overlapping region between the hot and cold composite curves tells us that we can recover 51.1 megawatts of energy. Um, and then and then the nearest nearest the vertical distance or closest vertical distance between the hot and composite hot and cold composite curve. This is what we call the pinch point, where the delta T mean of 10 degrees Celsius is located. So for this particular problem, our delta T mean is 10 degrees Celsius. So meaning at this point, the hot stream is colder. The hot stream is hotter than the cold stream by 10 degrees Celsius. Today, we will plot the grand composite curve. And in order to do so, we have to shift the hot and cold composite curve close to each other so that they would be touching at this pinch point. Okay. So previously, it's the composite curves are apart by 10 degrees Celsius at the pinch point. So we shift the hot stream by half a delta T mean. Okay, so as you can see, it was shifted down to half a delta T mean, and we will also shift the cold stream by half a delta T mean upwards so that they would meet, okay, at this point. So it means that the the hot stream is colder by 5 degrees Celsius and the cold stream is hotter by 5 degrees Celsius because of this shift. So now you can see that they are touching at the pinch. And we do this because we need to generate the grand composite curve. So this is the pinch. We do this because we need to generate the grand composite curves. But remember that we are not actually changing the temperature of the stream. So it's important to know that we just need to do this shifting of the temperatures to in order to build the grand composite curve. So let me show you. Okay. This is the graph of the grand composite curve. We have delta H at the bottom and the temperature. But because of the temperature shifting, we named the vertical axis as T asterisk, maybe to represent the shifted temperature, which is different from the original temperature of the composite curve, where here in the original composite curve, we use the actual temperature. All right. So now we begin the plotting of the grand composite curve. First, we take the horizontal distance in between the hot and cold composite curve. For example, at 250 degrees Celsius, the horizontal distance is 7.5 megawatts. So we plot the distance there, as you can see, 7.5 megawatts. Um, and we do this for every turning point. Okay, so this one is turning point. So we do that, and as you can see for the pinch point, okay, so that's a turning point. So as you can see for the pinch point, since they're touching each other, there's no difference. Okay, so uh we don't have to plot anything here because there's no difference between there's no horizontal distance between the hot and cold composite curve. So we proceed with the plotting of the horizontal distances. And then once that we have plotted all of the horizontal distances, we connect the lines. Okay, we connect the lines to end up with the grand composite curves. Now, here are some important features of or strengths of this grand composite curve. The segments that have negative slope, okay, so for example, this one, it has negative slope, uh, are energy generating. Okay, so whenever you notice a negative slope, when it moves down to the right hand side, this segment, in this particular segment, like this first segment, it means energy is being generated. Okay, and this is true for segments 1, 3, 5. Okay. On the other hand, uh, when the slope is positive, okay, so like this one, 2, 4, and 6, uh, these have positive slope, which means the arrows are pointing downwards to the left. So that means that here in these segments, the energy is being consumed, right? Okay, so energy is being consumed. Again, so when the slope is negative, energy is being generated. So the movement is downward right. When the movement is downward left, energy is being consumed. So as you will notice, so energy is being generated and consumed. It forms a small little triangle right here, and we call that pockets, heat pockets. Okay, so we call that heat pocket. Uh, so inside the heat pockets, we assume that there will be energy recovery. Okay. So this is where the process to process heat recovery happens. All right. So and next we need to remove that. And the moment we remove the heat pocket, um, what is left are these horizontal distances. Okay. So we take out the heat pocket from the analysis, and then we focus on the region where the heat pocket has not been removed. Like, for example, this segment right here, uh, in red color, the horizontal distance is 4.5 megawatts, and then here, the right here, the horizontal distance is 3 megawatts. So in total, this would make up the 7.5 megawatts in which we need the hot utility, right? And remember earlier, we identified the hot utility target as 7.5. So it means at these two levels, the 7.5 megawatts is materialized to provide heating for these two. Okay. And that is for the region above the pinch, where hot utility is needed. On the other hand, for the region below the pinch, which is below 145, okay, degrees Celsius, so it means that the hot pinch is 150 and the cold pinch is 140. And the middle of that is 145. Okay, so remember that we shifted the temperatures. Um, we also remove the pocket, and then there's a blue segment here. Okay, this blue segment, the horizontal distance is 10 megawatts of energy. So we need to remove that 10 megawatts of energy by using cooling utilities. Okay. So again, the direction of this segment is um, to the right. So there's energy generation. And the slope is negative, right? So there's no energy recovery needed, but there's excess energy that needs to be removed using cooling water, right? And that's equal to the 10 megawatt that we identified through targeting. Okay, so this is the uh, heat source and this is the heat sink. Right. Next, we move on to the utility placement using the grand composite curve. So in doing utility placement with the GCC or grand composite curve, what we need to do is regard uh, regard the hot utility as another hot stream that which has to be plotted on the grand composite curve. Okay. So um, when it's plotted in the grand composite curve, it has a supply temperature and target temperature, which are reduced by delta T mean divided by 2. So half the delta T mean. So remember, we shifted the temperature, okay, by half the delta T mean. Similarly, the cold utility is also regarded as a cold stream when it's plotted in the grand composite curve. It has a supply temperature and target temperature, but are raised by half the delta T mean. And that is because that's how we plotted the grand composite curve. We shifted the temperatures by half the delta T mean. So it's important to note that for the hot utility stream, okay, um, the temperature should be reduced. Okay, while for the cold utility stream, the temperature are raised by half delta T mean. So please note of that important distinction when you're plotting the utility on the grand composite curve. So let's demonstrate that in the next example. So the next example is this one. We need to determine the amount of hot utility. So given two levels of, first, we have two options. We have steam and hot oil. So we need to determine how much of steam and hot oil we need, okay, um to further uh raise the temperature of the cold stream. So under the steam option, we have two types of steam. We have the high pressure and the medium pressure steam. The high pressure steam is at 240 degrees Celsius, while the medium pressure steam is at 180 degrees Celsius. Right. On the other hand, our other option is using hot oil. Okay. And given here is the CP of the hot oil. And what we need to determine is the minimum flow rate of the hot oil at these two temperatures. So we have two options: supply temperature 280 and 250 degrees. So here we need to determine the flow rate of the hot oil. For the steam, we need to determine their load or the megawatts needed. Okay. So now we first let's try determining the load of the saturated the steam. Okay, the saturated steam needed. All right. So remember that our target is 7.5, okay, for the hot stream, and 10 megawatts for the cold utility, or the 7.5 megawatts for the hot utility and 7.10 for megawatts for the cold utility. So what we need to do is to maximize the steam, okay, um, of the lower pressure steam or the lower temperature steam, because that means that uh, this type of steam is cheaper compared to this higher pressure steam, right? So because it takes more energy to raise the temperature of the steam to 240 compared to raising it to 180. So if this is available, then we must maximize the temperature of this steam. So because we shifted the temperature, okay, um by 5 degrees the moment we place our steam on the grand composite curve. We need to shift it by 5 degree, half T mean, half of T mean. So that is 10 divided by 2, so 5. We need to shift it downwards by, or reduce it by 175. So remember, that's the rule that we take note earlier. So reduce it by half delta T mean. So instead of plotting it on 180, we plot it on 175. Now, what we do is draw a line, okay, all the way until it touches the heat pocket at this level, okay. So, we, so that means we approximately need to get the horizontal distance. We approximately 3 megawatts of 180 Celsius steam, okay. So, um, and that implies that we can reduce the requirement for the 240 degrees Celsius steam. Okay. So the 240 degrees Celsius steam, we need to shift it down to 235 because of the adjustment in the temperature. So we plot it there, and the horizontal distance is 4.5 megawatts. Okay. So if we're not utilizing so for example, we don't use the 180 degrees Celsius steam, so that means we need to use more of the 240 degrees Celsius steam, which is more expensive. But because of the usage of the low temperature steam, the usage of the higher temperature steam can be reduced. Okay. So it's like we're sticking with the cheaper option, right? And we can also consider doing what they call the cogeneration. Okay. So if we're going to perform a cogeneration, the cogeneration turbine can be placed at the 240 degrees Celsius steam, and its let down can get us the lower temperature steam at medium pressure. So that's an option. So we generate two types of steam and also some power from the turbine. However, this means that um, there's additional investment that we have to make if we want to consider this option. Okay, next we try the other option, which is the hot oil circuit. Okay, so this is done by supplying hot oil at two temperatures. One is 280 degrees Celsius and the other one is let me go back to that, 250 degrees Celsius. Right. Now, so we're reminded that our hot utility is bound to 7.5 megawatts, and that is the opening right here. Okay, so this is the opening right here. So let's say hot oil is to be supplied at 280 degrees Celsius, given its CP value right here. Uh, so what we need to do is to place the hot oil circuit at this point, 275 instead of 280 because of the temperature shift. And then located on the grand composite curve, if we want to minimize the mass flow rate of the hot oil circuit, uh, so next we need to determine that uh, we should actually keep it to the minimum because that would give us the minimum cost, right? And what we need to do is draw the steepest line, okay, from the pinch point to this edge of the rectangle right here. So what we need to do is keep it above the grand composite curve. So make sure that this line is above the grand composite curve. So um that's why at this point they're just touching. Okay, so they're just touching because we need to keep it above the grand composite curve. So doing this method would help us easily determine the flow rate of the hot oil. Okay, so how to do that? We just simply divide the enthalpy, okay, which is 7.5 megawatts, divided by the CP value. So since it's in kilojoules, so we just use the kilowatts instead. So divided by the CP and also divided by delta T. Okay, so that would give us, so that's the delta T is 275 minus 145, and that would give us 27.5 kilograms per second of flow rate. So this is the scenario when the temperature of the hot oil is 280 degrees Celsius. So what if the temperature of the hot oil is 250 degrees Celsius? Okay, so what we need to do, okay, again, take the horizontal distance and then plot the temperature at 250 minus half delta T mean. So that's 250 minus 5, 245, and make the rectangle. So just like before, we need to plot a steep curve fro from this inside the rectangle, but making sure that it's right above the grand composite curve. So it's barely touching this point. Okay. So because of that, the end of the line right here is raised. So before it's at 145, exactly the pinch point, but because it's because we plotted it um and by making sure it's above the grand composite curve and the temperature is lower, it does not um it does not reach the pinch point. Now it's the other end of the line is 155. So like so, we calculate the mass of the hot oil, okay? Um, and that is 7,500 kilowatts, okay, which is our hot utility divided by the CP and delta T of the oil. And here the delta T of the oil is 245 minus 155. And what do you notice? The flow rate 39.7 kilograms per second is higher than the flow rate of where in the scenario where the temperature is 280 degrees. Okay, so it's higher, and that's because um we need at lower temperatures we need larger flow rates to cover the entire heating of 7.5 megawatts. So obviously the flow rate is high in this case, but this is the minimum when the temperature of the hot oil is 250 degrees Celsius. Okay? So this is already the minimum, but if you use a larger flow rate, then that's okay, but it would entail higher cost. Right. So we move on to the next example, which is the termination of the amount of cold utility. Right. So let's assume two options. The first is cooling water, and then the other option is low pressure steam. For the cooling water, assume that it has the following properties. The supply temperature is 30 degrees Celsius. The target temperature is 60 degrees Celsius. And we have the CP of the water. Next, for the other option, the low pressure steam, um, because if we're not using cooling water, okay, so we can also make use of the low pressure or generate some low pressure steam because of the high pinch temperature. So assuming that the low temperature steam is to be raised at 120 degrees Celsius, so this is lower than our pinch temperature. So we can make use of low pressure steam. We just need to check how much of this steam can needs to be used. Right. So let's move to the grand composite curve. First, let's try the option cooling water. So remember our cold utility requirement is 10 megawatts. So um, we have to, okay, we have to remove 10 megawatts of energy to the cooling water. And what you want to do is to, of course, to minimize the flow rate of this cooling water in order to minimize the cost. So to do that, we make a steep line. Okay. Again, we plot this red line at the temperatures. Uh, remember our supply is 30 and our target temperature is 60, but because of the shift in temperature, we have to raise. Okay, so because we are now in at the heat um, source, we have to raise the temperature by the half the delta T mean, so that becomes 30 to 35 and 60 to 65. So we plot a steep line um, according to the supply and target temperature. Okay. And then next, we calculate for the mass of the cooling water. So just divide the enthalpy, which is 10,000 kilowatts, with the CP and the delta T, and we get the mass flow rate of the cooling stream. Right. Now, if you're not removing everything using cooling water, um, we can raise some steam. So the good thing here is our pinch temperature is relatively high at 145 degrees Celsius. So we can use a bit of low pressure steam. If the temperature of the low pressure steam is 120, so it can be used to cool some of the uh, hot stream. So below that that is below the pinch. Right. So again, um, since our steam is so we're now dealing with the region below the pinch. We have to raise the temperature by half delta mean. So our 120 low pressure steam is plotted here at 125, but still below the pinch temperature at 145. So remember that for the region below the pinch, so at this region, energy is removed by the cooling water if we're not using uh, low pressure steam. But if we are generating low pressure steam, we can also utilize that. So we measure the horizontal distance, that is 4.2 megawatts. Okay, and then the rest of the uh, horizontal, or the rest of the energy will be removed by the cooling water, okay, at the supply and target temperature. So we make a steep line right here. Okay. So that means we need to remove 5.8. Okay, so 10 minus 4.2, that means 5.8 must be removed by cooling water. Alright. And calculating the uh, mass flow rate of the cooling water, okay, um, we simply divide the enthalpy by the Cp and delta T, okay, to calculate the mass flow rate of the cooling water. And what can you observe? It's lower than the requirement earlier, so lower than this one. So the mass flow rate here is 46 kilograms, but in the previous example, it's 79 kilograms per second. So that means we're able to decrease the cost of the cooling water by using the steam that we dumped from the earlier process. Okay. Actually, this is the end of the module. If you're interested to know more about heat exchanger network, you can refer to this book by Robin Smith. It's published by John Wiley. This is the title, Chemical Process Design Integration. It has several chapters that extensively discuss the heat exchanger networks. Right. So thank you very much. This is now the end of our video.